Okay, this is our lecture that we had today in class for Monday, October 7th. It's on section 4.4, and we had a very lively discussion in class. It was great to have the question and answers going on. I can't really do that now with the audio. This is, of course, the exact same video or written presentation that you saw, but the audio is going to be a little bit different, of course, since I'm by myself. But I'll try the best I can to copy the live presentation, which you guys made really good with your wonderful questions and answers. All right, so to start off, we have this figure given. Line segment BC is congruent to line segment DA, and line segment BC is parallel to line segment AD, and we need to prove that triangle ABC is congruent to triangle CDA. You should have this all written down in your notes, so no need to rewrite this unless you were absent, of course. And, of course, anytime in the presentation, feel free to pause. All right, so what we want to do is prove the two triangles are congruent, and like we discussed today, our plan for proof is side angle side. We're going to start off with statement and reason, and our first statement almost always is the given. So in this case, we have BC is congruent to DA, and BC is parallel to DA, and again, that's given. And like I said, our plan for proof is to use side angle side. Well, we already have this side here, which is right here with the blue tick. BC is congruent to AD. So we've got that already down. And what we need now is an angle. And like we went over in class, we have these two parallel lines, BC and AD are parallel line segments, and they're cut by this transversal. So we can have this angle, angle BCA, is congruent to this angle, angle CAD. And to clear that up a little bit, we have these two parallel lines cut by a transversal. So I just kind of transposed that over here to hopefully make it a little bit more clear. So again, if you have two parallel lines cut by a transversal, by alternate interior angles theorem, these two angles must be the same. That's why I move over here and say, well then, BCA and CAD must be congruent, or their measures are equal. Okay, so we can state that now. Angle BCA is congruent to angle DAC, alternate interior angles, and we have now hold on, we have a side, and an angle. Right here's a side, right here's the angle, and we need another side. Remember, we want side, angle, side, and the angle is literally in between the two sides. That's the way it's written, and that's the way it will be on the figure, is literally in between the two sides. So the side that we obviously need is this side, AC. And we could say that, what happened? And we could say that line segment AC is congruent to line segment AC because of the reflexive property. I don't know what happened. Seems like everything got erased. I don't know what happened there. Anyway, sorry about that. I don't know what to do there, but once you can just pause this and copy all that down if you need to, and this should be a continuation. I obviously probably pressed an erase or something like that, or a swipe. So it's reflexive, and then we are now free, since we have side angle side, we can say triangle ABC is congruent to triangle CDA, and that's because of side angle side, and you can of course just abbreviate it as SAS. Okay, the next concept is the hypotenuse leg congruence theorem. This theorem can only be used for right triangles. That's important. It can only be used for right triangles. And it can also be abbreviated as HL. And so if you have two right triangles, and these are right triangles because we have these red squares that denote that we have two 90-degree angles, or two right angles. So by definition of a right triangle, if we have a right angle in it, then it must be a right triangle. So we have two right triangles, and then we have the two hypotenuses are congruent to each other, and we have the two legs are congruent to each other. And so we can say that triangle ABC is congruent to triangle DEF. And that's called, again, the hypotenuse-leg congruence theorem. You can just abbreviate it on a proof as HL. So copy this down. This is the figure that we'll be trying to prove. This is the given. Given AC, line segment AC rather, is congruent to line segment BD. And angle ABC and angle DCB are right angles. And basically what I have written under the given is also this right here is also displayed in the picture, right? AC is congruent to BD, that's with the tick marks, and angle ABC and angle DCB are right angles with the red squares. So we want to prove that triangle ACB is congruent to triangle DBC. So let's start off with the statement and reason. We have angle ABC and angle DCB are right angles, and AC is congruent to DB, given. Step 2, triangle ACB and triangle DBC are right triangles. As we went over in class, and we've discussed this in previous chapters as well, and as I mentioned right here, it's just a moment ago, we have the reason for this statement, statement number 2, is definition of a right triangle. And so now, if we have two right triangles, we don't have to use SSS or SAS. We can just go straight through and use HL. I would rather use HL because that's only two things I need to look for and not three. So we have BC is congruent to BC by the reflexive property, and let me go back there. So we have BC is congruent to BC, and we also have AC is congruent to DB. And if you go back to the figure here, we can see that we have AC is congruent to BD, and that's given. That's with the tick marks. So we have those two are congruent to each other. And then we have BC is congruent to itself, reflexive property. So we have hypotenuse and leg congruent to the hypotenuse and leg of the other triangle. So going back to this, we have BC is congruent to BC, and AC is congruent to DB. Again, we have these two here, and because of those, we have hypotenuse leg, and we can say that therefore triangle ACB is congruent to triangle DBC, HL, hypotenuse leg. So that's the end of that lecture 4.4, and hopefully if you missed it, this will help out. And like always, if you have any questions, come see me and I'm sure we can clear it up. Thank you. Bye-bye.